are with Johannes de Jong of the KONE elevator company, and we're talking about a huge technological innovation in building transportation systems. One of the Council's innovation winners this year is KONE UltraRope, which is going to enable future elevator travel heights of up to 1 kilometer. So the kilometer-tall building is here, and you have the stuff. This is it.
This is it.
This is it. Tell me about UltraRope.
Well, UltraRope is an extremely light, very strong rope, very durable, fire-resistant, and because of its lightweight, it will take away approximately 90% to 95% of the rope weight away in buildings with travels of more than 500 meters, elevator travels of more than 500 meters. So it takes a considerable amount of weight away from the elevators, weight that we have to move around, weight that uses energy. And we can reduce the energy consumption therefore dramatically as well.
What would the kind of cable that they're using now, if we put it next to this, what would the difference be in size and weight?
I would say weight-wise, this is about 90% lighter if you talk about a 500-meter high building. And so if you would have, let's say, 20 tons of ropes, you can bring it down to maybe something like 2 tons of ropes, which is a dramatic 18-ton reduction in rope weight.
The development process for this and the story that you've told me about is the R&D process for this was in a sauna, is that right?
Yeah,
actually. How is this done?
It actually started in a sauna. We had this entrepreneur guy who started building his very first carbon fiber rope in the sauna. He did it in the sauna because you needed heat to actually put it together. And he used the heat of the sauna, a typical Finnish story, done at home in your sauna, in the heat of the sauna.
Carbon fiber, we're talking about carbon fiber, and those of us who read science fiction, you know, we've been told about carbon nanotubes, for example, for a lot of years. This is carbon fiber, but it's not carbon nanotube, is that right? What's the difference between the two?
That's correct. Carbon nanotubes are just the next generation of carbon fibers in principle, which are just much stronger even than carbon fiber. Carbon fiber is already extremely strong, but the costs of nanotubes become really too big if you think about normal elevator usage. If you think about special usage, such as things as the space elevator, yes, then you absolutely have to go into nanofibers.
And that's the stuff of science fiction stories. So this is kind of the first manifestation of that technology. What's the difference in the production process between the two?
Well, it just is a question of how you put it together. The production process here doesn't require too much microscopic work, where if you go to nanotubes, you actually are putting together molecule by molecule on top of each other. So it's an incredibly expensive process. But
the price will undoubtedly come down. How close are we to that?
Well, to be honest, carbon fiber, we have been talking about carbon fiber prices coming down dramatically already for 20 or 30 years. They have come down, but not dramatically. So one of the things we know from carbon fiber is that costs are still a lot depending on the availability of materials, and this cleanness of materials still actually has quite high costs related to it.
What is the production process for something like that?
Well, when we have here the bars, we have in principle a lot of vertical carbon fibers, which we hold together with a matrix. I won't say the material here, unfortunately. I can't say that, but we hold it together with a matrix that actually makes a solid bar. And then we hold all the bars together with the high friction coat. We need the high friction in elevators anyway because of the fact that we need friction to get the counterweight and car, which do not have the same weight, working on a traction shift. So we need a lot of friction, and this has a lot of friction.
So the rider experience in a car with a cable like this, in an elevator cab with a cable like that versus traditional, is it user or transparent to the user, or what's the difference?
The only thing the user may notice is an even more silent ride, because the coat is very silent compared to steel on steel, which we typically have in a normal elevator. So it is more silent. And the other things the user will not necessarily immediately notice, but when you're going very high, ropes can actually, especially on windy days, they can move around in an elevator, actually pulling up the car a little bit, so you can feel that in the quality of the ride as well. This has much higher frequencies, will not resonate with the building frequencies, and therefore again gives you a more silent, more quiet ride. So in general, a more quiet ride.
So in a configuration in a super tall building, how wide is the cable going to be? How many of these sections in that?
Depends on the size of the elevator, depends on the height of the elevator, of course. But typically we will be using between 10 to 15 of these cables side by side. Yeah.
In one layer, one ply layer?
No, just side by side.
Right, okay.
Yes.
Interesting. They're talking about this extending the range of elevators to 1 kilometer. Is that truly the range? Is it more expansive than that, or how do you know the true range?
With this technology, it's easy to go to 1 kilometer. Yeah, that's not a problem anymore at all. That can be done now. It's just a question of getting newer technology into use. We are actually changing the elevator. This technology allows us to change the elevator again and do things which you could earlier not do with a normal elevator. So I can't talk too much about that, but the elevator will change a little. It will become a little bit easier still to do even higher things and bigger things. So this allows that as well at the same time. It allows runs of up to 1 kilometer. So if you would like to go to the top of the building, it means less transfers. Like for example in Burj Khalifa nowadays, you may need to make 2 or 3 transfers before you finally get to your final location, and transfers take time. So getting there in one shot is always helpful.
Getting there more quickly?
Getting there more quickly. There are limitations to getting there more quickly as well, which is the human body. Yeah? The human ear, unfortunately, is a valve, and it lets air out quite easily, but it doesn't let air in that easily. And this causes problems. You need to swallow actually when you get very high. And if you do that too quick and you miss your little border where you need to swallow, and your pressure starts building up in your ear and it becomes uncomfortable. So that's the limit actually.
One of the ways elevators can change, of course, is more than one cab, and there are some double-decker elevators out there.
Yeah.
Are we going to see more cabs? Is that one way elevators will change? Potentially?
This will actually make triple decks quite easy. So having 3 cars on top of each other would be possible. The problem there becomes then how to handle 3 doors at the same time. So we will see that elevators become more like trains, less like elevators, that you can influence the doors. So it simply means that doors will have to work like in trains. They will have to close, force close. And in that way, yes, triple deck, even quad deck would be possible in the future.
They've been talking for many years about elevators that move horizontally as well as vertically. Is this compatible with that kind of movement?
Well, we've been talking about possibilities for the future. One of the possibilities moving horizontal for a while is giving people time to adapt the ears. And so we move them fast to their location and then actually use the horizontal movement to adapt. Give them some time for the ears to depressurize or to pressurize in the right way, and then let the passengers out. So it would mean systems where we have multiple cabs and then vertical movement there.
Are we still looking at a scenario where you can liberate the elevator car from the elevator shaft?
That's the plan.
That's still good with this.
That's still doable, and that is definitely things we have to look at when we go extremely high.
It seems like you're hitting the industry with this at kind of a crucial time, because we are starting to see building designs that are a kilometer tall, a mile tall.
Yep.
Is the timing pretty fortuitous here? Is it a coincidence or no?
It is partially coincidence, but partially also we had these high buildings inside. We knew that the 1 kilometer building was coming. So we knew that we had to start looking for technology that could do a kilometer high building. This kilometer high building has elevators which have travels which were never done before. And I still think that doing it with steel ropes is not really that great. It uses an incredible amount of energy to do it, while this would use a lot less energy. But if we go to the mile-high building, then we will see travels of up to 1 kilometer possible within one go, which means twice Taipei 101 stacked on top of each other in one go. So now we have to really start looking at technology that can do these kind of things. We were stuck at 500, 600 meters approximately with conventional ropes. Now we can get there.
So we were truly up against the wall, up against the height limitation of the old technology when this comes along.
Absolutely. You know, when we were looking at the skyscraper 150 years ago, the skyscraper was enabled by the elevator. Yeah, and if we now look at the problems, actually, the elevator is now becoming the bottleneck for the skyscraper, and this actually solved the bottleneck. Well,
you can't. The developers and the designers and the engineers can't do anything without you.
That's correct.
Can't do anything without you. So you obviously have to be cognizant of the trends that are coming forward. A lot of people have been surprised by hearing about a kilometer tall, a mile tall building being seriously discussed. Probably a lot less or a lot more time for you to know that that's truly serious. How long have we seriously been looking at that?
We have been working on UltraRope for 9 years. So this is not something that just gets born in overnight.
You knew this was coming.
We knew that something was coming. Yes, we knew that buildings are getting higher and higher. And you just need to follow the statistics of the council. And you just see that elevator or building heights are going up exponentially. The number of high-rise buildings is going up exponentially. So this becomes a problem. One has to find better ways of doing it.
And of course, all of this comes as no surprise to you.
No, it doesn't.
No, absolutely not. As far as retrofitting old buildings, how easy to convert to the new technology?
It takes a bit of engineering, it takes a bit of work. We've just done it at Marina Bay Sands, which is now the first building in operation using UltraRope. It's been doing that now for a month at this moment. And immediately we took out about 3,000 kilos of ropes. That's 3,000 kilos immediately gone. And we reduced the energy consumption by approximately 15–20%.
So for the John Hancock Centers and the Willis Towers of the world, these buildings are 40 years old. What's their impetus for going to this technology?
It's all doable. What you need to do is either you change the machine or you change the traction sheave, you change the compensation sheave, and you change a couple of hitches, and you can use this machine technology. It's not that big a job.
And the big benefit is energy savings. Is there more to it than that?
It's energy savings. It's being less sensitive to building sway, practically inert to building sway. You don't need to shorten the ropes anymore. This rope doesn't densify like normal steel ropes do, so you don't need to shorten them after a couple of years. You don't need to replacing it is also much easier. It doesn't weigh very much. Changing steel ropes is it's a very elaborate job. Takes a lot of days, and the elevators are out, reducing your usage of elevators. This is just, so much easier in the end.
So 9 years in development, was there a point where there was really a breakthrough, where this kind of got critical mass, where there were some hurdles that all of a sudden were solved?
Getting the shape, getting the function of UltraRope was actually a small job. It was about 1 year, 1.5 years. We knew immediately how to build it. The big job was to test it, making sure that it performed, that it was safe, and that it did what it was supposed to do for super high-rise buildings. We tested it rigorously. We tested it at high speed in our test shaft, the Tyttöri mine shaft in Finland, 1,000 feet deep. We could run it at 15 meters per second, 3,000 feet a minute, to check that it would really work at such super speeds. It does it. It works fine. We did friction tests. We did aging tests, because this material ages. So we had to see how it performs with aged materials. Still, under aging, it did exactly the same. It was very, very good in its performance. We did fire tests. we must make sure that it can withstand at least the same kind of situations as steel ropes.
As good as or better?
This is actually better. This performs better than steel ropes in fire conditions. We had to check that we had the energy consumption reductions which we estimated, and we checked all that. We had to check how sensitive it was for foreign particles to enter the system. You know, we're in a very rough conditions, construction industry, where you can have stones, whatever, falling between tools, you know, going between the rope and the elevator system. So we just had to make sure that it could withstand all that.
Is there different maintenance? Is the maintenance easier with this technology?
The maintenance is of course slightly easier. You need to monitor it, yes? So we have a system with which we can monitor it all the time, in real time, which will tell us whether it is getting worse or not. We expect this to last easily 20 years, yeah? So in our tests we have done incredible amounts of bendings without this thing ever even fatiguing.
What's the life expectancy of the current steel cable?
When you go super high like the shears tower, you're typically starting to talk about the lifetime of the ropes getting shorter and shorter, because you actually need to use steel to carry steel, so you're reducing your safety factor to as low as you can, and that also has an immediate effect on life. So in the high-rise buildings as we see them nowadays, one can typically expect that a 400 or 500 meter travel, you have about 4 or 5 years of life. If you want more life, then this is the way. This has about 15, 20 years of life easily.
So Johannes, I'm going to ask you to look into your crystal ball, or your carbon fiber ball. Mid-century, 40 years from now, what are tall buildings going to look like, and how will people move around in them because of this?
This will change it. There will be more changes, I'm pretty sure about that. It's everyone's goal and everyone's desire to actually be independent of ropes in the future. Yeah? This will enable to go further up to that stage. But still, the last goal is get rid of the ropes altogether. Have multiple elevators running in the same shaft. That is the future.
And this is the stuff that will do it?
This is the start.
Okay,
Yeah.
and what's the next step from here, do you think?
The next step from here is ropeless elevators. Multiple elevators moving independent, all in the same shaft without ropes.
So the way that we're thinking about elevators is due for a radical shift starting now.
When you talk about 40 years, absolutely.
Absolutely. Thanks for coming to see us in Chicago.
Thank you.